Welcome to the deep dive. Today we're jumping into a stack of sources on what are, well, probably the most extreme objects in the entire universe. Quasars.
They really are the cosmic lighthouses. And if you want to understand the absolute bleeding edge of physics, this is where you have to look.
Absolutely. When they were first cataloged, I think back in the 50s, they just looked like faint stars.
Yeah, totally unremarkable points of light in photos. That's where the name came from. Quasi-stellar radio sources.
Or QSRs for short.
Exactly. But that name, star-like, couldn't have been more wrong.
And that brings us to the central paradox, the thing that really defined the 1960s for astronomers.
It's a total mind bender.
How could something that looks like a single point of light?
Yeah, and it's coming from a region that's, what, maybe the size of our solar system.
Right. And yet it's radiating more power than all the stars in our galaxy.
All of them combined. It broke all the known models of physics at the time. It was a scale mismatch that made no sense.
So that's our mission for this deep dive. We're going to unpack the engine that powers these things, look how their discovery literally redrew the map of the universe, and explore this weird temporal mystery of why we mostly see them in the distant past.
It's a great story.
Okay, so let's start with that engine room. To outshine an entire galaxy, you can't be using the normal power source, which is, nuclear fusion like in our sun.
No way. Fusion is. It's just not up to the task.
Why not? What's the fundamental problem?
It all comes down to efficiency. I mean, fusion is amazing for a star like our sun, keeps it stable for billions of years, but it's actually kind of wasteful.
Wasteful how?
A star only converts a tiny fraction of its mass into energy. We're talking just 0.7%. To get the kind of light we see from a quasar, you'd need a mechanism that's just orders of magnitude better at turning mass into raw power.
So we need something way, way more efficient.
And that's where you get into the world of extreme gravity. The answer is a supermassive black hole, an SMBH.
Okay, so instead of nuclear reactions, we're talking about, gravity itself creating light.
Pretty much. You're converting gravitational potential energy into radiation. And it is wildly, wildly efficient. Depending on the black hole's spin, you can convert anywhere from about 5.7% all the way up to, theoretically, 32% of the mass of whatever falls in.
32%. That's, compared to 0.7% for fusion, that's a staggering difference.
It is. It's like comparing a leaky faucet to a hydroelectric dam. And you need that kind of power conversion to explain what we see.
And this requires a truly mind-boggling amount of mass to begin with.
Oh, absolutely. The SMBHs that power quasars range from millions to, in some cases, tens of billions of times the mass of our sun.
Billions. And that mass density is the smoking gun, isn't it? It tells you it has to be a black hole.
It has to be. There's no other way. If you tried to pack, say, a billion suns worth of mass into a space the size of our solar system.
Like a really dense star cluster or something.
Yeah, it would just collapse on itself. The stars would collide constantly, and the whole thing would inevitably form a black hole anyway, so you might as well start there.
So the energy isn't coming from inside the black hole because nothing gets out of that.
Correct. Nothing escapes the event horizon. The light, the energy, it's all generated outside the black hole from the material spiraling in.
Accretion disk.
The accretion disk. You've got gas, dust, even shredded stars all swirling into the black hole, getting compressed and heated up by friction.
I mean, you say heated up.
I mean, millions of degrees. It's so hot it glows brilliantly across the entire spectrum. X-rays, visible light, radio waves, you name it.
Wow.
And the scale is just, look, a billion solar mass black hole only needs to eat about 10 suns worth of material a year.
Only 10.
To produce the light of 1,000 normal galaxies.
1,000 galaxies worth of light from just 10 suns a year. That's just... I can't even picture that.
It's the most efficient engine in the universe.
So if all that energy is radiating out from this hot disk, what about the jets? Some of these pictures look like they're firing giant lasers into space.
Ah, yes, the jets. A fantastic feature. Not all quasars have them, but the ones that do are spectacular. They shoot out these incredibly straight beams of particles.
And they're moving at what speed?
Near the speed of light. And these jets can stretch for millions of light years, way, way beyond the host galaxy itself.
So how does the disk create these focused beams?
The powerful magnetic fields in the accretion disk basically grab charged particles and funnel them outwards, perpendicular to the disk.
Perpendicular, so your viewing angle suddenly becomes really important.
Crucial. If you're looking at the quasar and the disk is edge-on, the disk itself can block some of that intense central light. But If one of those jets happens to be pointed right at us,
We're staring right down the barrel.
you're staring down the barrel, and we call that a blazar. It's the same object, fundamentally, but the light is dramatically amplified by relativistic effects because it's heading straight for you. It's all a matter of perspective.
So the physics is incredible, but the discovery story is just as wild. I mean, back in the early days, the big challenge was just figuring out where to point your telescope.
Exactly. You had these radio surveys, like the 3C catalog, picking up these strong radio sources, but they were just points on a map. You had to match them to something you could see in visible light.
And you needed really, really precise coordinates for that.
Painstakingly accurate. Places like Caltech's Owens Valley Observatory finally gave them the precision they needed to pinpoint objects like 3C273.
And that's where Martin Schmidt comes in 1963. He gets the spectrum for 3C273, looked at the emission lines, and they make no sense.
None at all. They didn't match any known element. He was apparently just stumped for weeks staring at these weird spectral lines.
Until the big breakthrough moment.
Yeah, the story goes he was sitting in his office and it just clicked. He realized they were familiar. It was the Balmer series of hydrogen, the fingerprint of the most common element in the universe.
But they were just completely in the wrong place.
Horribly out of place. They were shifted by a massive 15.8% towards the red end of the spectrum.
He famously told his wife that night, something terrible happened at the office.
And the terrible part was the implication. If that redshift was because the universe is expanding,
A cosmological redshift.
then 3C273 wasn't some weird star in our galaxy. It was billions of light years away. And to be visible from that distance, it had to be unbelievably, terrifyingly bright.
And that one realization just instantly changed the scale of the entire known universe.
In a single afternoon.
So this is probably a good moment to ask, for you listening, how do we even measure a distance that huge? I mean, the usual method, parallax, only gets you out to maybe 50 light years or so.
Right. You need a better ruler, and that ruler is spectroscopy. It's all based on the Doppler effect.
Like an ambulance siren?
Exactly like an ambulance siren. As it moves away, the sound waves stretch out, the pitch drops, light does the same thing. As a galaxy rushes away from us, its light waves get stretched to longer, redder wavelengths. It gets redshifted.
So you look for a known fingerprint in the light.
A specific spectral line. For instance, the hydrogen beta line always emits light at a wavelength of 4,851 angstroms. That's its home base.
An angstrom being a very, very tiny unit of length.
Very tiny. But when Schmidt looked at 3C273, that line wasn't at 4,851. It was way over at 5,615 angstroms.
That's a huge stretch.
A huge stretch. And from that, you can calculate the redshift, which we call Z, and using Hubble's law, that tells you the distance. In this case, it came out to over 2 billion light years.
So that single measurement of stretched hydrogen light completely redefined cosmology.
It opened up the deep universe.
Which brings us to the temporal paradox. Looking far away is looking into the past. So, are quasars still a thing today, or did we miss the cosmic party?
The short answer is we kind of missed the main event.
Oh.
The peak era for quasars, what some people call cosmic high noon, was about 10 billion years ago.
When the universe was only, what, 2 or 3 billion years old?
Exactly. Back then, they were thousands of times more common, more active than they are today. The universe was just blazing with them.
So what happened? Why the big decline?
They ran out of food. It's as simple as that. These things are incredibly hungry. Over billions of years, the supermassive black holes just consumed all the easily available gas and dust in their immediate vicinity.
They starved themselves into silence.
And became quiescent, dormant, just like the black hole at the center of our own Milky Way, which is very, very quiet right now.
The very earliest ones,
Mm-hmm.
they pose a huge challenge for our models, don't they?
Oh.
I'm thinking of this quasar, J0313-1806.
Ah, yes, the current record holder for distance. We're seeing it as it was 13 billion years ago.
So that's only 670 million years after the Big Bang. The universe was an infant.
It was, and the problem is the mass of its black hole. It clocks in at 1.6 billion solar masses.
And that's just too big, too soon.
Way too big, too soon. There's a physical limit to how fast a black hole can grow. It's called the Eddington limit.
Right, because as it feeds, the light it gives off actually pushes back on the material trying to fall in.
Precisely. It's a self-regulating process. So even if a black hole started growing right after the Big Bang, and it fed at the absolute maximum possible rate, it couldn't get to 1.6 billion suns that quickly.
It's a mathematical impossibility.
By standard models, yeah. It just doesn't work. You can't grow that fast from a normal stellar mass seed.
So that forces us to rethink how these things got started.
It does. And the theory that's really gaining ground is something called the direct collapse scenario.
Okay, what's that?
The idea is that in the very early universe, you could have these huge, pristine clouds of hydrogen gas that didn't form stars first. They just collapsed directly into a massive black hole seed.
So they skipped the whole star is born, star dies, black
Yeah.
hole forms step.
They skipped it entirely. And these seeds wouldn't be 10 or 20 solar masses. They'd be 10,000, maybe even 100,000 solar masses right from the get-go.
They got a massive head start.
A huge head start. And from there, it's actually plausible for them to grow to 1 billion solar masses in just a few 100 million years. It's a fundamental shift in how we think the first giant structures formed.
So putting it all together, quasars are basically the spectacular, explosive youth of most big galaxies.
That's a great way to put it. They're powered by these hyper-efficient black hole engines, and they acted as the first lighthouses, letting us map out the deepest, earliest history of the cosmos.
And it's not just ancient history. We have one of these dormant engines right in our own galactic backyard.
We do. Every big galaxy, including ours, has a supermassive black hole at its core. Ours is just sleeping.
Which leaves us with a really provocative final thought. Our quiet galaxy isn't going to be quiet forever. We're on a collision course with Andromeda.
Yep. Our nearest major galactic neighbor. The big crash is scheduled for about, 3 to 5 billion years from now.
And when that galactic merger happens, all that chaos is going to do what?
It's going to funnel enormous amounts of fresh gas and dust right down into the center of the new combined galaxy.
Fresh fuel for our sleeping giant.
Fresh fuel, and it's very likely that this new supply will reignite our central black hole, turning the good old Milky Way
Into a brand new, spectacular quasar.
It's a pretty dramatic finale to look forward to for our corner of the universe.